Hey there, it's your old pal, Mr. Cook. We're going to go through the supplemental review for Unit 1, one page at a time. So let's get started on it. Okay, so we need to state whether each of the following represents a function. So when we have a list of coordinates like this, what we'd want to do is check to see if all of these follow the idea of what makes a function, and that comes from the vertical line test. Even this graph over here, this graph, all of these kind of follow that same kind of idea of vertical line test. And what it means is that for every x value that you have, you should only have one y value, and that's it. If you have another y value, then it's not a function. Okay, so if we go over to the very first one, we just look at the x values, 1, 0, -1, and 0. Notice that 0 occurs twice. So if this is a function, then that means that the y value should be the exact same. Since it is not, since these values are not the same, then that means that this is not a function. So that's pretty easy. And then for this one over here, if we do the vertical line test on the graph, at any point along the graph, looks like that any vertical line that I pass through this graph will not touch more than one place on the graph of the function that I have. Even this spot right over here where I have like that open circle and that closed circle, that just means that like the vertical line goes through that open circle, and the only intersection place actually happens at the closed circle right over there. Okay, so that's true over here as well. So this passes the vertical line test. So this is also a function. All right, now let's take a look at this one. Well, x minus 5, the absolute value, I'm sorry, not absolute value, the square root of x minus 5, I would just graph that out and see how it looks, and then see if it passes the vertical line test. So I'd hit y equals, and then square root, and then x minus 5, and graph. Looks like my window's been affected a little bit. Let me go to zoom, and then 6, that puts it back into a standard window. There we go. So it looks like my graph is just going to continue to go up and up and up and up like that. If I zoom out a little bit even, I see that, yeah, it just continues to go out like that. So it'll pass the vertical line test at every point because there's not a second graph underneath it. Okay, so this is also going to be a function. And this one says graph, then determine the parts, the intervals listed below. So we have an absolute value function, so let's graph that out on our calculators as well. Let's go back to a standard window, so zoom and then 6, and then we'll type that in. So f of x is equal to absolute value of x plus 4, so we hit y equals, and then we go to absolute value. On my TI-84, I hit the math button, and then I go to the number column, NUM, and it's the very first thing, absolute value, and then I just type in x plus 4, so x plus 4, and graph it out. Okay, so there it is. If I want to get a little bit more specific, I can get some coordinates from there. So I hit second and then graph. I have my table. I can just graph a couple of those, like -4, 0. So over to the left 4, up 0. -3, 1. -2, 2. And so on. Looks like it's just going to go up and to the right each time in this direction. Now I'll move my table up a little bit more and see what the other one does. So I have -5, 1, -6, 2, and so on. So it goes up and to the left each time. Okay, so there's my absolute value. Easy enough. All right, my domain is all the possible x values that I can plug in. So here's a really important thing to remember with domain. We only have 3 restrictions on domain in this class, and you'll see them as following. If you have a rational function, in other words, a function over another function, like this, in other words, if x is in the denominator, all you want to do is make sure that whatever that function is, the whole thing cannot be equal to 0, and then you solve for your x values, and then you'll tell what the domain is. I think that we'll probably have a couple of examples of that later on, and if not, I'll do a couple of those from maybe the textbook or something like that, just for some extra practice. And then the other one was if we had a radical and a function underneath the radical, and if that was the case, then we had to make sure that the function under the radical had to be positive or 0, so it had to be greater than or equal to 0. Then we'd solve for the x values, and that would be our domain. So the nice thing is that this absolute value isn't either of those, So that means that we can go to our standard default for the domain, and that's all real numbers. So going from negative infinity to positive infinity. If you wrote either of those, that'd be fine. All right. Or if you just wrote all real numbers, x can be all real numbers, that's fine too. Now for the range is all the possible y values that we get from coordinates on the graph. And it looks like the lowest possible y value that we're going to get along the y-axis is over here at 0. And it looks like it just keeps going up and up and up. So every other y value is going to be accounted for in the range. So that means that we start at 0 and it's all the positive values after that. So that means my y values just have to be bigger than or equal to 0. And writing that out in interval notation looks something like this. So we start at 0 and then go all the way up to infinity. And remember, infinity has the little parentheses because it doesn't include that value. Now with increasing, decreasing, and constant intervals, these will all have parentheses around them, okay? So no brackets like that anywhere on here. When it's increasing, it's going up and to the right. Another thing about the intervals where it's increasing, decreasing, and constant, we are only talking about the x values, and that is it. Only x values here. So for the increasing part of it, going up and to the right, it starts at this coordinate and then just keeps going, forever, seemingly up and to the right. So the x value is at -4, so we start at -4, and since it keeps going forever in that direction, it goes to positive infinity. So again, we just put parentheses around those and we're done with that interval. Decreasing means it's going down to the right, so it's going down to the right starting off the graph, and then all the way up until -4. So when it starts off the graph, it's going to keep going in this direction. So I could start like way, way, way off of the graph, and it'd still be decreasing as I get to this point. So that means that I'm starting all the way as far as x can go in the negative direction, so negative infinity, and then all the way up until x gets to -4, it's going to be decreasing. All right, so constant is where I'd see horizontal parts of the graph, but there's nothing like that here, so I don't have to worry about it. There is nowhere where it's going to be constant, so I can just write nowhere in there. Relative maximums or relative minimums. So that just means like the lowest possible point that you see in a given like small interval. I don't think that we're talking about absolute minimums or absolute maximums. So it's really just like whenever you see like the bottom part of a hill or the top part of a hill on a graph, that would imply that you have a maximum or a minimum. We'll see some weird stuff in this graph, and I'll talk a little bit about this graph as well. But in this case, we just have a minimum, which is at the bottom of the hill over here. And if you just look at the graph, it's located at -4, 0. So that's our minimum, -4, 0. You can use your fancy graphing calculator functions for that, but it's going to be the same value. Just the, spotting it basically helps you out. As far as maximums, there isn't any like top of the hill kind of moments. The graph just keeps going on and on and on, up and up and up forever. So there's really no maximums that we see. So there are none here, or you could write NA, just something like that to get the point across that we know that there aren't any maximums on this graph. All right, now on to this graph for number 5. Well, here's the deal. So this graph is actually like way more complicated than anything that we would give you on a test or on a quiz. This is just, again, one of those moments where we're giving you homework, and this is even optional homework. So it's, we can challenge you a little bit and see how you kind of respond to it. So I'm going to graph this out and then show you why it's kind of ridiculous and why we would never put something like this on a test. I'm going to make a fraction. So I hit alpha, y equals, and then graph. Okay, so there we go. And then we got 2x to the 3rd power, and in the bottom it's going to be x to the 2nd power, or I can hit the square button there. There we go. And then -4. Okay, so there's my graph, and then I just hit zoom and then 6 to make sure it's on a standard graph going 10 by 10. And here's how my graph looks when it's all done. Okay, so kind of looks like a cubic that's been reflected over the y-axis for this part of it. So, that's how I'm going to graph it. So 0, 0 there, and then looks like the graph kind of goes through maybe a couple coordinates. Let's go to the table and see if we have any like whole coordinate answers there. Doesn't look like it. It's a bunch of fractions so far. Yeah, it looks like I'm going to be kind of guessing on how this graph looks. That's one reason why okay, we're going to have an entire unit, and I think the second part of first quarter, yeah, it's unit 2C. We talk about rational functions, and we'll know how to graph that really, really well. we're gonna have a ton of practice with it. But for right now, just kind of guess, how your graph's gonna look. It's gonna look like, something like that when I'm all done. We won't, we would never have anything like this because we wouldn't be able to really judge how you graph this too well. So, take that as it is. But check out what happens to this graph a little bit later. So I'm going to zoom out, just show you how it's kind of like an interesting graph. You zoom out a little bit. So it looks like it's a linear equation. Then some funky stuff happens. And it's like back to a linear function. Pretty weird stuff, right? Yeah, that's why, again, we would never ask something like this. But the domain, basically, you can use all real numbers for it because with one exception over here. So I guess this does have some significance for stuff that we're working on right now, and that it creates a domain restriction for us, because this is one of those ones that I was talking about. It's a rational function where we have a function on top and then a function in the bottom. Now the function in the bottom is what gives us the domain restriction. So what we do is we just take the bottom part, x squared minus 4, and we say that it cannot be equal to 0. And then we just solve for all the possible x values that would, make it 0. The reason that the bottom part can't be 0 is because if it ever is, it breaks a math rule. We'd be dividing by 0. So we can't, do that. We can't let the x values make it so that the graph is dividing by 0. So we solve for x, add 4 to both sides, we get x squared cannot be equal to 4. Take the square root of both sides and we get x cannot be equal to plus or minus the square root of 4, which is 2. So there's our domain. X cannot be equal to negative or positive 2. Now for the range, so yeah, based off of that graph, you can see it gets, kind of funky looking. Look, there are range restrictions as well. They have these things called asymptotes that you get to, and I think that this actually might have a, let me see, there's a slant asymptote, and it might have a value that you can take out of there, because if you saw over here when we hit the table, we have errors for where x is equal to 2 and x is equal to negative 2. So yeah, there's like some crazy stuff there. So the range on this one is kind of, if you just base it off of the graph, it would be all real numbers. But like I said, in Unit 2C, we'll circle back to that and we'll see exactly what that looks like. All right, anyways, now for the last couple where we're just checking to see if we have even or odd functions. These ones should be pretty straightforward, and then you have to state why afterwards. So with even, odd, or neither functions, what you do is you plug in negative x and see what happens. Okay, so with an odd function, every single one of the terms will change sign. With even function, none of the terms will change sign, and with neither, neither of those situations play out. So it's pretty straightforward. So if we plug in negative x for h of negative x is equal to negative x to the 4th power plus 3 times parentheses negative x to the 2nd power plus 1. So negative x to the 4th is like saying negative x times negative x times negative x times negative x. That means that there are 4 negatives that are multiplying. So if it's a negative times a negative times a negative times a negative, that ends up being a positive number. So this, when you have that 4th power, it ends up canceling out the negative, so you just end up with x to the 4th. Similarly, if we do negative x to the 2nd power, it's negative x times negative x. So the negatives cancel out there, and we end up with a positive x squared, so 3x squared. And then we just have that plus 1. It's not even affected by the negative x. So if you notice, when we plugged in negative x, we ended up with the exact same equation that we started with. If that's the case, then that means that we have an even function. Every single one of the terms need to stay the same. If even one of them changes, then that means this is no longer an even function. Here's a real easy way to check for it as well. If you pick, it won't prove that you have an even function. You still need to plug in negative x, but just to kind of check initially to see if you're going to get an even function or an odd function, you can just plug in a number and then its opposite. So like if I plug in 2, into the h function, and if I plug in negative 2 into the h function, so x and negative x, 2 and negative 2, I should end up with the exact same answer. So I want you to, just go ahead and try and see if that's the case. Since it's an even function, that should be the case that you get the same number. All right, now let's take a look at this one. So we're going to plug in negative x for f, and we get negative 3 times parentheses negative x to the 3rd power plus 4 times parentheses negative x and then plus 2. Negative x to the third power is negative x times negative x times negative x, which gives you a negative overall. So that negative will multiply times this negative 3 and will give us a positive number overall. So we'll get 3x to the third there. And then negative x times positive 4 gives us a negative 4x. And then we have that plus 2. Okay, so now we plugged in negative x, and let's see if it's even or odd. So the first term, the sign has changed. Okay, so that means that we could have an odd function, and it immediately tells us that it's not an even function because the sign's changed. But now if it's an odd function, then every one of the term's signs should change. So negative 3x squared to the third power changes to 3x to the third power, so the sign changes there. And positive 4x changes to negative 4x here, so that's good. But 2 doesn't change. It stays as 2. Every single one of the terms needs to change for it to be an odd function. So that means that this is going to be one of those neither or neither, however you pronounce it, functions. All right, so that's the end of the first page, and then we're going to continue on to the second page in a second.